So welcome everyone to this 13th seminar of the 13th week of this seminar series on mechanics of materials. So today we have Professor Ankit Srivastava from Texas A&M University with us. So I'll give a brief introduction of the speaker. So Dr. Srivastava obtained his bachelor's degree in mechanical engineering from Kamala Nehru Institute of Technology, Uttar Pradesh in 2007. And master's and PhD in material science and engineering from University of North Texas at Denton, USA in 2013. So after spending a couple of years as a postdoctoral research associate in the School of Engineering at Brown University, he joined the Department of Material Science and Engineering, Texas A&M University as an assistant professor in 2015. So Dr. Srivastava's research combines experimental and computational methods for mechanics and material science to unravel the deformation and failure mechanisms of materials with evolving microstructures. The overarching goal is to relate the statistics of a material's microstructure and loading conditions to its deformation and failures, and develop statistically informed models for materials design. So I would like to thank Dr. Srivastava for accepting our invitation to present the seminar, and I'll hand over the floor to him. Before that, I have one announcement for the participants. If you have questions during the talk, please type them into the Q&A box, and we'll take questions in turn at the end. So with that, I think I'll invite Dr. Srivastava to take the floor.
Thanks, Shyam. I hope everybody you can hear me, right?
Yes.
So I really like to thank Shyam for the introduction and for hosting me today, and special thanks to Dr. Sumit Basu for his invitation. It's really an honor, largely because of the organizers and for the long list of people who have given talk before me. So what I'm going to talk about today is simply the idea is to come up with a method to correlate the microstructure of a material and fracture. I'll give a brief overview of things that we have done in the past that led to the final method, and I will talk to this very simple method, be rather a simple talk in general. Majority of the work was, this works, yes. So this work was largely done by my graduate student, Abhilash Mulkeri, who is in his last year of his PhD, and a large amount of contribution was made by my PhD student who graduated earlier this year, Yu Liu. And part of it was also done by Jinsu, who is also in her last year of PhD. This whole work started while I was still a PhD student with Dr. Alan Edelman, who started looking at microstructure-based fracture modeling and trying to predict or correlate microstructure and fracture properties, especially crack path and crack growth resistance. The work was done earlier in collaboration with Shumil Osowski, who was postdoc with Alan when I was a graduate student, and he's now faculty at Department of Mechanical Engineering at Technion, Israel, Haifa. So with that, I'll take this opportunity also to give a little overview of my department, Material Science and Engineering at Texas A&M, largely to give a context. When Shyam was a graduate student at Texas A&M, the department did not exist. So it's a rather new department. So I'll just plug in this advertisement a bit. The university, Texas A&M University, is one of the oldest, or the oldest university in the state of Texas, starting in 1876. But the material science department started in 2013. And within a short span of 7 years, we now have around 18 faculties, including 4 National Academy members, which is one of the biggest honor in United States. That includes 2 well-known names in mechanics, Alan Edelman and George Farr. Moving on, we have a plethora of research field of interest to any graduate student will be structural materials in the mechanics community, extreme materials, materials for extreme environment, and computational material science, together with experimental mechanics at a smaller scale, largely led by Dr. George Farr, since he joined our department. As of fall 2020, you can see we have a good mix of number of undergrads and PhD students, so it's very research-oriented department. The equal mix, we're now ranked 14 in the graduate program as per US News. This is among public universities. And This is an old picture of the department. Most of the students and faculties in the department, and for the first time, I see my graduate students in the first row. At least they're in the first row somewhere. But now we are big enough so that we don't fit in one frame. This is the website. If any graduate student out there or want to know more about the department, they can visit. I really like this statement. This statement was written for this piece of art that is in front of our new undergraduate education complex. Says, from the outside looking in, you can't understand it. From the inside looking out, you can't explain it. This is pretty much is what we know about fracture. From outside looking in, you can't understand it. From inside, you can't explain it. So with this statement in mind, I'll just summarize what I understand about fracture as an introduction to, I think, maybe one person in this audience who is not actively involved in fracture. So a simple fracture story. Let's consider a blob of material. It's a piece of gray metal, let's assume, or any material that has a crack in it. The fracture mechanics basically says, I got a bad guy who is the driver trying to open the crack, and I have a good guy sitting inside the material that is trying to resist the crack growth. So in the Star Wars terminology, I got emperor and I got resistance. As long as the bad guy loses and the good guy wins, the crack stays where it is. Once the good guy loses, the bad guy wins, the crack starts to grow. It's a pretty simple story. The balance of two forces, one is driving force, one is resistance force. When the driving force overcomes resistance, crack starts to grow. What's the big deal about it? Nothing much to know. Other than the fact that the materials are not this gray blob of piece. So each material has this heterogeneous microstructure. And as you see, when we brought this microstructure in, both the good guys and the bad guys become happy because the microstructure can help the good guy. Microstructure can also help the bad guy. A bad microstructure that nucleus damage easily will make crack grow easily. A good microstructure that good and bad remains qualitative in this case and debatable, but we'll just go, a good microstructure can also help the good guy. Largely because once you have a crack tip and a microstructure, the driving force, the stresses that form, once you apply, say, a mode 1 small scale yielding loading condition, you get a stress field or strain fields that develop ahead of a crack tip or in front of the crack tip that affects the microstructure. The microstructure evolution in this case means evolution of damage, or you may have phase transformation and things like that. And this evolution of microstructure affects the crack path. So it's a coupled cycle. Which one is affected more, which one is affected more will depend, do we get more resistance or it's become easier for the crack to grow? Well, more often than not, we know from material science perspective, a crack in the material follows the microstructure. So microstructure does have many roles. It's also make the crack grow in certain way. So if we look this way, oh, it is helping the bad guy because there are features in microstructure that allow the crack to grow easily. But then also there are features in the microstructure that trap the crack or move them around. So the simple goal of this thing, which is not my goal, I didn't come up with this statement. It's there for a very long time. It's 100 years of fracture mechanics. At least since last 60 years, everybody realized the role of material microstructure. So what is the relation between the observable, where observable here simply implies relevant features of a material microstructure and its resistance to crack growth, and how do we predict it? Now, the how do we predict is not something for the first part I'm going to present is anything new. It's been there. All I could do is I got better computers and better codes to run these calculations. So how do we do it? Final element, well known. So this has been there for a while. What we're going to do is take a specimen, small scale, mode 1 small scale yielding boundary value problem. So I'm applying loading condition that represents mode 1 small scale yielding condition. I got a notch and I got a small region where I'm going to model the material microstructure. And what I'm going to present is a simple microstructure. Either I have these inclusions, these tiny particles that nucleate voids, or I have this nice distribution of grain boundaries. And the crack in this case is driven by grain boundary. So that's intergranular fracture. Or in this case, is an inclusion-driven fracture. Matrix of the material is isotropic, elastic plastic. And the method, we're going to use finite element explicit. We take this thing, put in the finite element code, which is a dynamic, follows the dynamic principle of virtual work. So finite element explicit. Why explicit? We're interested in quasi-static. Explicit because we're going to simulate crack growth. And it's not easy to make an implicit code converge. So we go with dynamic principle of virtual work. As long as we follow things in explicit calculation right, we get a reasonable convergent result. And since we're doing dynamic calculation, but we're interested in quasi-static fracture, we apply initial and boundary loading conditions such that it minimizes inertial, which is basically the wave effects. So we got the method, we got the model. Now we need the constitutive method. So constitutive framework, basically we're going to rely on ductile. We're going to model ductile fracture. This is what I do. We're going to focus on wide nucleation, growth and coalescence, and that leads to formation of a crack. So this is the basic premise. And how do we mathematically write it? It's not new. Started with Fred McClintock and Rice and Tracy's seminal work, analyzing the growth of an isolated void in an infinitely large medium. Later, this thing was put in terms of a flow potential or a yield function by Gerson in his PhD thesis under supervision of Professor Rice. Once Gerson finished his thesis, two-person, Viggo Tvergaard and Alan Needleman, took the Gerson models and put it in a finite element code. And in 80s, they modified the Gerson model, which is now referred to as a modified Gerson model, or is also known as the GTN model, Gerson Tvergaard Needleman model. Basic, simple idea. We have a material, a pore in it, and the deformation, we apply a boundary value traction or displacement, and we divide the deformation in two parts, elastic, plastic, not a big deal. We're going to modify the plastic part to account for this variable F, which is the porosity or void volume fraction coming from nucleation, growth, and coalescence. This could be also pre-existing in a material. And phi is my flow potential, Mises effective stress, and epsilon bar dot is the strain rate, effective plastic strain rate. If F goes to 0, this goes down to simple von Mises material. So we got F goes to 0, dP reduces down to plastic strain rate in a von Mises, isotropic von Mises material. All right, how the void evolves? The void volume fraction, the first part of this equation follows mass conservation. Then I have a second part introduced, the part of work by Shu and Needleman that introduced nucleation of voids. So you have this discrete microstructure feature that nucleate void, these voids grow. So this gives you an early jump in the voids, and that they follow, the further growth of them follows these mass conservation. The flow potential, as was written by Gerson, is here with Qs introduced by Viggo Tvergaard. And this last part is what makes fracture possible from these models. What we have is that we say, okay, this depends not on F directly, but on a pseudo function F star, which is simply the void volume fraction coming from growth and nucleation. But nucleation in a way violates the mass conservation, but let's keep it there. F, that this enters here, you have the flow potential that start to shrink. When F grows, the flow potential start to shrink. And if F is greater than some critical value, then this growth of F star becomes asymptotic or near asymptotic. That causes the collapse of this yield function rather rapid. Before we go on, simple, if this F star goes to 0, you reduce back to a von Mises flow potential. This is actually a flow potential, so I should not have used equal to 0 sign, but we have it there, like a yield function. All right, so when the yield function starts to collapse, just visualizing in simple uniaxial tension term, I got elastic, yielding, strain hardening, ultimate tensile strength, that necking in an axisymmetric bar. Then I have this damage region where the voids start to grow. I reach this point where majority of material points have reached F greater than Fc. My yield function start to collapse rapidly and the load bearing capacity drops rapidly, which basically mimics the creation of a new free surface or fracture. So with that, I need one more thing, the definition for plastic strain rate, which is simple power law. It's a very favorite. And hardening is, again, a simple power law, metallurgically very old. So we put these two things, easy. Now I need nucleation criteria, because if I have a microstructure feature, they might not have a void, but they may nucleate void as the deformation proceeds. So I got a material, I got microstructure, and the nucleation criteria follows two relations. Either I can have a nucleation coming from accumulated plastic strain, as shown in this material, or I can have a nucleation of void coming from a hard particle or a soft particle. One follows around mean strain. I have a mean equivalent plastic strain. If I reach that value following a half Gaussian distribution, I nucleate voids. Or based on stress, I have this driving force, effective stress plus hydrostatic stress. In summary, it's a scalar measure of a maximum principal stress, a very approximate zero-order approximation, but gives you a driving force for stress-based nucleation. With that, it's done. So now in a simple way, I will show Okay, this is, once I have pointer on, it doesn't work. So I need to go back to, all right. So some simple simulation results. We're focusing on the small box. I have inclusion. I had the notch here and the crack starts to grow. We could do this for different inclusion sizes. These are size, this is double the size of the initial size. EX is the mesh size. And ignore, I have the volume fraction of 2%, around, this is around 0.19, pretty large volume fraction. And we can simulate these three-dimensional crack growth paths. We can calculate from these calculation the JR curve or the crack growth resistance curve. This is the J integral J. This is driving force in this case, applied J as a function of increment of crack, delta A. And this J, because we're imposing K1 field, so we have K1, which is directly imposed, and we can follow simple Rice's criteria and get J and plot J delta A curves for all these cases. So we can simulate, we can estimate crack growth resistance curve like one would do in ASTM or in simple experiments. These are thin slice of material, but I forgot to mention that the front and the back face of the specimen was under plane strain conditions. So 3D microstructure, but it's still overall plane strain. That allows me to even define a J1C. So then I can take the J delta A curve, mimic an ASTM standard where I fit a power law and I draw a line, get an offset. So that gives me crack growth initiation toughness, which is the J1C value. I can plot this data with microstructure parameters. So I can now correlate crack growth initiation toughness with volume fraction of inclusion, size of inclusion. And here is a set of experimental results from multiple ductile materials. These are not for one set of material. Our model wasn't calibrated at all to match any one of these. This could be just serendipitous, but exciting to show that the results predicted by the calculation shows realistic comparison with experiments. And these experimental results were summarized in one of the paper by Professor McMcKay. So we can get nice realistic inclusion-driven fracture simulation. Moving on, these microstructure-based can also be done to analyze other simple scenarios like a microarchitectured material. This work was experimentally done by St. Pierre when he was a PhD student with Vikram Deshpande at Cambridge. Took a slab of aluminum, drilled a bunch of holes, laser, put a notch, and did this 3-point bending fracture test. He had one hole, multiple hole, and we did the finite element simulation for this problem to see that do we have J field and all other things, can we define fracture properties and things like that. So this is a simulation result. Easily we can model discretely these voids and we can let the crack propagate, and we can then plot these values with respect to the hole diameter and spacing in a single row of hole, and in this hexagonal row of hole, which is the microarchitecture material, and look at its fracture toughness. So in this case, I'm just comparing the results with experiments. This is single hole case, solid symbols are experiment, and two open symbols are one applying mimicking ASTM standard or the experimental procedure to our simulations to calculate KJ1C, fracture toughness simply, or directly measuring, drawing a contour and measuring J integral. Remember, these are 3-point bending, so I don't have a K field imposed a priori, so I cannot directly compute J, but I can do simple contour integral. Either case, we get a very nice comparison with experiment, single hole, row of hole, nice. The idea was here in the microarchitecture material, we get nice comparison experiment as well, actually slightly better than what we got in single holes. And we showed nicely that with this microstructure-based modeling, we could design lattice materials or this architecture material that are 50% lighter than parent material, but maintain the same fracture toughness. This denominator is the fracture toughness of the parent metal, which was aluminum 2000 series. Now, when we can plot simple ASV map, here are the lines that represent our lattice, our microarchitecture material. And you can have a material which has a density less than that of water, that's 1000 kg per meter cube, and a fracture toughness greater than 10 megapascal root meter. That was pretty neat in this case. We also did grain boundaries. We're talking about grain boundaries. These holes were just a little bit of sidetrack. But we also can do grain boundaries. We focus on metastable titanium beta alloys. We can simulate crack growth. These hair-like features are visualization errors, so we just ignore it. And we get realistic crack paths like what you would see in experiments. The crack follows the boundaries of the prior beta grains along basically the alpha grain boundary alpha. And we could extract J delta I curve from this simulation. We can get tearing modulus, which is nothing but a normalized slope of these curves, plot them with respect to strength of the grain, because strength of the grain is what we can make. We can change the precipitated structure in a grain, and we can actually make in experiment grains with different strength. And by increasing the strength of the grain, we can increase its strength, overall strength of the material by designing the precipitate. But when we increase the strength of the material, we lose. So these also provide a nice qualitative comparison, realistic comparison with experiments and inform us. We did this simulation before we did this experiment with Pacific Northwestern National Lab. All right, so simple summary with the microstructure fracture modeling takeaway. The microstructure-based fracture modeling can provide realistic, I have it in quotes because we never try to really validate these, but it looks realistic, provides a scaling relation, and provides a way of designing. So realistic prediction of fracture behavior from the material microstructure and material properties, which is not directly possible if you apply the widely popular and actually not only widely popular, widely successful engineering fracture mechanics based approaches, then you can't really get microstructure inside. These are not that popular, they're hard and not straightforward, but seems to have promise. These can also provide basis of designing material, as we saw in terms of grain boundaries, strength of material, and microarchitecture materials. Moving forward, we have seen a lot of advances in design methodology. Basically, the idea of the holy grail of material science is a designer gives me target performance matrix, and I come up with a material that meets that performance matrix. That means I got to solve an inverse problem. Now, a lot of focus has been done in improving elastic modulus, yield strength of the material, nothing much, and nothing on high toughness. The few paper on this topic was focused on getting in a homogenized sense, how much volume fraction inclusion I should have. But there are some work done in that regard, largely because optimizing microstructure to enhance material's crack growth resistance requires optimizing topological feature of the material microstructure. Now, topology optimization is not a new thing. It has been there for a while in aerospace field and in civil engineering, but those topology optimization features structural topology optimization. Now, the question would be, in the terms of a computational mechanics person, what's the difference between structural topology and microstructure topology? Not much. The only problem is that it's just too complicated at a microstructure scale because the constitutive models are complex, modeling requires very fine meshes, and becomes rather complicated. Means calculation becomes expensive and not really realistically doable. So we cannot really use these things that I've shown so far, microstructure-based fracture modeling, with any of these optimization, which are generally an iterative scheme, to solve this problem and design a material with higher or enhanced fracture toughness. It just becomes unrealistic. So there is a need to develop computationally efficient fracture modeling scheme to correlate materials, microstructure, and its crack growth resistance, so that one could really use it in designing. And also these microstructure-based calculations are only limited to people who have optimized codes and access to good computational resources. As I talked before, simple, intuitive, cracks follow microstructure. So all we need to do is to find the crack path and estimate the energy invested in following that path. That's all we need to do. So do we really need to follow the full field boundary value finite problem? Maybe, maybe not, but it seems like maybe you can get away with that just by doing a path search. So how do we do a path search? Now, coming back to the well-known part, Google Maps. Google Maps does path search. This is a snapshot of Google Maps. And how does Google Map does path search? A simple example, I'm focusing on, this is Anushakti Nagar. I worked for 2 years at Bhabha Atomic Research Center. That was my favorite part in India before leaving India for graduate school. So I'm just going to focus and show an example of Anushakti Nagar. We picked up the North Gate canteen, which is a canteen at the entrance of BRC, at the gate of the Bhabha Atomic Research Center. So we go from North Gate canteen to Gateway of India. Plug in these two locations and Google Maps gives me a path. Done. Pretty easy, straightforward. It also tells me the shortest distance path, depending on what the features you have in your Google Drive or Google Map app, shortest time path, estimated time to arrival. Now, the total time taken, let's say, and the estimated time to arrival is analogous to crack growth resistance. The time coming from the resistance itself, which is the traffic. And I have a well-defined network of road. Google Map just picks the path, which if you put time biased path, it does weighted directed graph. If you just ask shortest distance, it does directed path. So Google Map can do it, we can do it. All we need to do is find a path. So let's see, what are the challenges in actually doing or mimicking a Google Map for fracture? Now here is my small scale mode 1 problem, right? It's a large level specimen, small scale loading. I got a notch, I got a material here. Remember, Google Map searches and finds the optimum path in a well-defined network. Highways are well-defined, and Google Map knows where the highway is between a source and a target. So basically your starting point and your end point based on a certain criteria, shortest distance, shortest time, and so forth. So Google Map has these two. So let's focus on one simple microstructure, a case of intergranular fracture, grain boundary driven intergranular fracture when I have a connected microstructure. Do I have a source? Yes. We're doing a mode 1, so I got a crack tip, I know my source. Do I have a well-defined network? Yes. I'm saying that my crack will always follow grain boundary, and I'm just focusing on 2D, so I got a nice well-defined network. Do I have a target? No. I don't know where I'm going. Crack doesn't know a priori what's going to end up on the right side. Do I have a criteria? Well, we don't know yet. Now, if I go to a discrete microstructure, the second part that I was talking about, inclusions. Do I have a source? Yes. Do I have a well-defined network? I don't. I just have a point in an open field. Do I have a target? No. The criteria? Well, we don't know. So what we do? It's a hopeless situation. But instead of giving hope, let's start one by one. Let's make my problem similar to Google Map problem. How do I do that? Just for the sake of validity and developing hypothesis. I'm going to focus on this where I had no target and I don't know my criteria. I want to build a path. And how do I know where my target is? Let's do one thing. Let's solve a finite element problem, a full field boundary value problem, and see where my crack is going. So I get this solution from a finite element problem, similar to what I was showing before. It's the same piece of work we've been doing in 2015. I have my source, and now let's pick the target from the finite element path. Once I have my source and target, I need a criteria. So what I'm going to say, by representing each grain boundary junction as a node, so all these triple junction as a node on a directed graph, that is movement is only allowed in the increasing x-axis. This is my x-axis. Together with the knowledge of energetic cost of propagating crack between the two nodes. Now just keep in mind, we'll come back to this one. That means I somehow know the energetic cost of propagating between two nodes, which is each grain boundary step or edge or facet. So just keep in mind, we'll come back to this one and discuss more. But for now, let's assume we know this thing. And we need to then do simply a criteria. So what we're going to do, we can find all possible crack paths and their crack growth resistance curves can be calculated utilizing a graph search algorithm. If I have a criteria, I can do it. This is what Google Map does. If I know the cost of every step, that's the traffic on every piece of road. If I know that, I can do weighted graph and I can find the path. Simply the algorithm Google Map follows. I do need the criteria though. I don't know shortest distance. I don't know shortest path. Richard Feynman once said, if you give me all the possible path between A and B, I can tell you the path of shortest energy, minimum energy. So let's draw from that. And since I know all the path, so I can find the path of least resistance between S to T. Now this is the crack growth. Black line is the crack growth resistance curve predicted from finite element. Red is the path of least resistance. It underpredicts the total crack growth resistance, and it underpredicts more and more as we keep going on. That means the crack do not follow the path of global least resistance. And if you think about that, it makes sense because crack doesn't know a priori where my target is. The crack doesn't know the target. It cannot minimize anything and cannot give you path of minimum resistance. Crack follows some other criteria, which we don't know. But anyway, we found out that even if we can come up with the target, Google Map doesn't work. So what do? Crack growth resistance curve and crack path differ significantly. This is the same statement that the crack path is not a path of least resistance. So what is the crack following? So we came up with 3 hypotheses based on all the work we did till date, or till 6 months ago. This is a very recent work. We haven't published yet. We're still working on this. The crack growth resistance of a crack propagating through a microstructure network can be described by microstructure-specific discrete units. How and why? Simply because if I take the path that the finite element gave me, and if I know the energetic cost, then I can just sum each part and get the curve. If I do that, this is the blue line. It matches. So if I know the unit cost of propagating each step and I know the path, then I know the curve. I don't know the unit cost yet, and I don't know what gives me path yet. So I don't know. But if I know those, I can find out. So my crack growth resistance through a microstructure network can be described by microstructure-specific discrete unit events, at least in the circumstances where I know what feature crack is following. And for a given crack path, the crack growth resistance curve can be calculated using the crack growth resistance of a collection of unit events. This is what we believe as a material scientist or engineer. This is what I just showed you is possible if I know. The crack path through a microstructure network is dictated by the local minimum crack growth resistance at each microstructure specific discrete unit event, and not by the global minimum crack growth resistance. This is what is, once I tell you, and once we talk up for it for 30 seconds, it becomes obvious. It's not something we are pulling out of the field. It's obvious. Crack doesn't know where is, crack knows A, crack doesn't know the target, doesn't know the B, but crack knows what is immediately ahead. So the only difference is cracks A and B are really close apart. They're the distance between the next possible microstructure specific event. I still need to find out what will the local minimization would be, that we don't know yet. And how do we define these specific discrete units? All right, so moving on, let's focus on the most complicated one that we started, where we know the only source, we don't know the target, we don't know anything. So let's take these discrete unit events and let's build a graph. We can build the graph like Google Map does because we don't have a graph. So let's come up with graph. How we're going to build graph in this case is just by relying on the things that we have learned so far. We know that the 2 times the mean inclusionist spacing is what dictates the fracture toughness from 3D calculation that I did, we published in 2014, from work done by Rice and Johnson decades before that showed that between 2 voids, 2 times the mean void spacing tends to dictate the critical crack tip opening distance. So, okay, let's focus small piece of the microstructure at a time. I'm only going to focus on a region that is within the 2 times the mean inclusionist spacing. Now I have certain inclusions, and I'm going to connect all these inclusions with direct straight lines from my crack tip. So I'm going to simply draw these vectors connecting my source to all these points. I'm just drawing 3 in here. So I got this P number of points, which are a subset of the total inclusion that lie within this 2 times inclusion, mean inclusion spacing. And I draw these arrows, which are my edge vectors, EJ. Now, once I have these edge vectors, I have momentarily the graph, right? Then if I have connected microstructure, it's even easier, right? In this case, I have only 2 possibilities. Each of these are triple junctions. So I have only 2 possibilities, 2 vectors, easy to define. So I can build my graph part by part by part. So in this case, I'm just focusing on what is the immediate ahead 2 edges. In this case, I'm focusing on what are the inclusions that lie within this 2 times inclusion. Now, this 2 times is really rooted in the mechanics of fracture mechanics that we know till date, correlating microstructure and crack growth resistance. All right, so now we need to know how the crack propagates. Now the crack propagation in this case, we'll define simply that now the edge vector, out of the 3 vectors that I drew, or 4 or 5 that could happen, that could be drawn within the limit of 2 times d inclusion, the crack vector, the crack chooses the vector at time t plus 1, which basically gives the minimum value of this function g. And this function g is basically a function of, is basically related to dj, which is the increment of crack growth resistance, which should be a function of the distance between the 2 and its angle of inclination. What that means, we'll come back, where the distance is nothing but the magnitude of these vectors, and the angle is nothing but the projection of these vectors in the crack growth direction x1, which will be this straight ahead. Projected crack growth is what matters. It's going to break my specimen into 2 pieces. And once I know all these ECs at every time step, I can simply sum up their projection, and that gives me my projected crack length, that what we measure in experiments or we rely on ASTM analysis. Once I have these all unit events of these G's, I can just sum total of them, and that will be my J at any given time T. I can do the same for this connected microstructure. The challenge here is that, okay, this stays the same. What is my G? G slightly changes. The equation may seem complicated, but this G definition is actually easier. All I have is that dj is no more a function of dj. So this d subscript ja, or the distance, is outside, and my increment of per unit projected crack length is a function of the inclination alone. So a little bit more complicated, a little bit simple. This is what we said, right? We're coming up, but I'm going ahead because we tried a lot of things and we came up with this function. So these two functions is what we now need to know. So let's go back and do finite element calculation, like the type of calculation that was done before. Following unit event. It's like analyzing one void ahead of the crack tip, borrowing from what was done by Fred McClintock and back in the days, looking at the growth of a void in front of a notch. We're going to analyze evolution of damage in one microstructure feature. So this is what I draw. This is my finite element model. This is simply plane strain 2D. I have 4 inclusions. My crack grows from this point 0 to 1, 1 to 2. I can define growth from 1 to 2 as the absolute distance between 1 to 2 and its inclination theta. I can get the increment or delta j, j2 minus j1, when crack grows from delta a1, that's delta a1 is this, to delta a2, that's this projected distance. I can get this delta j, and I plot this delta j as a function of theta, that's inclination, and d, and it depends on both. And it's not very simple, nice, clean function. But that's why we just chose this data. And anytime we use this unit event, we're going to just interpolate from this 3D plot. So we're not giving DJ any functional form. Now, there is no need because we have these discrete unit events as a function that we can come up with from the finite element. Then we run a simple finite element where we have a grain boundary step and inclination. These simple unit event calculations are really very simple compared to what we have been doing before in terms of full microstructure. Then I plot this slope. D change in dj over, this is simply delta a2 minus delta a1, that's d cos theta, which is nothing but delta a2 minus delta a1, normalized by sigma naught squared over e. And I get a function of theta. This parameter doesn't depend on d. So this is d is already enters in the normalization. This normalized quantity is simply a single function of theta. So this problem is slightly simpler. Now I got my unit event, I got everything, right? I know how to build my graph, I know how to choose one, I know how to grow cracks. And so with that, let's see how this predicts. So this is my model. I got this inclusions here, and I have this spacing. I know all this spacing. This video here will show you the crack path predicted by finite element. This video will show you crack path we predict from graph model, and this will show you the evolution of J delta A. Now, this graph model takes input from the unit event calculation. This is a full field finite element simulation. To give an idea, this full field finite element simulation takes 24 hours on a 20-core computer, and this on a single core will run in 15 minutes. All right, so I start to build my graph. This is an evolving graph. Every time I know my crack tip, I build my graph or a bunch of vectors, and I pick based on the criteria we define. We get a very reasonably close crack path predicted from graph model as the finite element calculation. And we also get very nice correlation in the overall fracture toughness. Now, one trick here, I'm not plotting the initiation value. So this is, I'm assuming my crack growth has begun. So this is, I'm just focusing on crack growth resistance, not the crack growth initiation resistance. So J1C is subtracted. We'll come back to that challenge later. All right, this is for one inclusion spacing. We did it for many, and this is the same. Let's go to next. This is 8, slightly more inclusion, and we do the same thing. Now, remember that if you note, the graph model and the finite element movies are not time synced because we have only fewer time steps. These are really bulky calculations. So that's pretty much it. These calculations are. There's very nice correlation between, sometimes we miss, like finite element didn't take this inclusion, graph method said take this inclusion. The difference is because this is based on the reference frame, and here the frame keeps evolving, right? So there's some still approximations. Now, how does it work in grain boundaries? This was the easier problem, so it work even nicer. Every time I have to only pick either this or that, right? So it's pretty easy to pick, and we can keep doing. We get very reasonably close grain boundary paths, fracture path, very reasonably close J delta A curve. We done for this. This is for rather large grain size. We did it for a smaller grain size. This is half the grain size that I showed the movie before. Again, but every time I reach a triple junction, I have to pick this or that, and it does pretty good. In grain boundaries, we most often end up picking what we want. Again, these are 2D calculation, 2D prediction. We're not at the 3D yet, neither Google Maps. So we already moved the algorithm beyond one day at a time, one thing at a time. So I'm just showing more demonstration thing. It's not only simple to some some simple grains. We can have anisotropic grains, elongated grain microstructures, and we can still predict nicely. These are elongated grain. My crack started from, let me get the pointer, started from here when this side. And this one, crack is still here. I rotated the grain, elongated grain by 45 degrees and showed this nice local minimum is what shows the model prediction. And then these two FE results. Works very nicely, even for very anisotropic grain structures. We have done a lot of them in multimodal grain distribution and show the predictions. So this here is, I have 2 grain distribution in these layers, smaller grains, larger grains, smaller grain, larger grains. And we do very nice predictions from these whole thing. We also came up with the obvious answer. Well, if you increase the grain size, toughness increases. We're known for 50 years. But we also came up with the non-obvious answer that decreasing the grain size in one layer and increasing in other layer so that the average grain size stays fixed has a greater effect than just increasing the grain size as a whole. This second part is important because sometimes we need strengthening from the finer grain, and we can then get toughening from the larger grain. Now, in summary, we have the emergence of advanced manufacturing technologies. It is becoming increasingly possible to control the microstructure features and characterize the microstructure features in 3D. So we need simple techniques to be able to correlate microstructure and crack growth resistance and crack path. So simple models, the graph search can be really good to design microstructure that then we can make or characterize the toughness of a material that we are characterizing from these advanced characterization techniques. So now, our simple and computational inexpensive model correlate relevant features of a material's microstructure and resistance to crack growth, and it can be easily used in iterative and non-gradient optimization schemes. Additionally, the model can be used to predict the path and resistance of any crack growth process that discretely propagates from one micro feature to another one. I saw there was a question. Sometimes Google Maps send me to road closer or circling paths from Vigneshwaran. So the question is, how does your method guarantee the crack actually propagate to some unknown target instead of going back? The reason I'm answering this question because I don't, and I had this thing here. Happened to me as well. You're not alone. Google Map once took me on a joyride for 10-mile long joyride, just turning around multiple pieces. All I needed to go take a U-turn. So the hope would be that this method can allow to have this. Right now, this method would not give you. So I guarantee you the method wouldn't predict this because it can't. It's a directed graph. It will always move in the forward direction. Google Map gets confused only when you try to take a U-turn. Can we make this Google Map confused by designing microstructure? Can we make crack follow this path? So that's pretty much it what I have. This is the group members. This is the name of my group. This is the link. Any student out there interested in the research, anyone could visit. Thank you.
Yeah, thank you very much, Ankit. It was a very interesting talk. So I think you have already answered the question that was posted on Q&A. So if anybody else has a question, you can either type in the question or I can allow you to talk. So it's now open for questions. Okay, I think it'll take a few minutes for people to type the questions. So in the meantime, I can ask you my question. Yeah, can you hear me, Ankit? Yeah.
Yeah.
So yeah. So and was it was the method is interesting, but the one question that I had is in order for this to work, you need to know at any given point in the crack. At any given point, you need to know the locations of all the. If you're looking at ductile fracture, you need to know the locations of all the second phase particles in the immediate neighborhood of the crack tip, right? So basically, you need, in order to use this method, you need a full map of the inhomogeneities in the material, right? If not, it won't work, right?
Yeah, the thing is, not only you need the full microstructure detail, you also need the unit events. So I remember when we were doing it, this basically the idea of this unit event and graph search started when from Shumwell-Osowski, when we're looking at grain boundary. And he came up with, in the grain boundary context, that we could come up with these unit events and predict these things and do this graph search. At the time, he was just looking at the first paper. He was basically looking at, can we find the crack growth resistance from these unit events? Will these add up to give me finite element equivalent methods? And then the second paper, when we went on, still focusing grain boundary case, the idea was we won't know. So we did one calculation, well, he did that, on taking the standard deviation. So let's say I know the standard deviation of the grain size and aspect ratio and things like that, and then try to predict a variation on the fracture toughness. And it showed that the method works, it gives you a spread and works reasonably well connecting to finite element simulations. So if we had experiment where I had the statistical knowledge of distribution, then we can run multiple of these graph search calculation and get some statistical idea. But again, you know, it still rely on unit events. So it's not there yet. We can't predict fracture pretty much. It's good to get qualitative trends.
Yeah, and I guess you can also use it to, I mean, make statements like what you made about that microstructure with two distributions of grain sizes, right? I mean, you can make design predictions like that. Assuming some,
Right, very qualitative, those type of predictions we could do, we can do. Right, and like in 3D printing, sometimes you have very dominant defect structure that you model, then maybe we could quickly say how you're gonna print the holes. So we started doing this on drilling holes in a sinusoidal path. At Technion, the experiments were done. We were looking at those sinusoidal modeling. We did modeling before we could get the experiment. And with that type of problem also, we could solve a priori that we didn't know this method before. So we ended up doing all the calculation for all the sign distribution of particles. Now, if I had to do it, I will just quickly get an estimate and do only a few calculations just to compare them.
Okay. Okay, we still don't have any questions in the Q&A box. So the other question that I had was regarding the G function that you showed, which is used for the local graph search, right? So I believe that G is the energy cost associated with choosing each particular branch, right?
Right. So that's simply the cost of DJ. So G is a function of the vector.
Yeah, so I mean, I can imagine that it will for a brittle fracture problem. I mean, I would think it's easier to come up with this G function, whereas for ductile fracture, the energy cost, the major contribution to the energy cost also comes from the larger plastic zone, right? So do you how do you if you want to solve this ductile fracture problem, how would you choose the G? Is it calculated computationally or is it?
Yeah, you're right in that. So what we found, this was the interesting part. The same thing came in our mind. This is ductile fracture, right? So the matrix follows Gerson. And we did this calculation, right. But this is small scale yielding, yeah. But you're still right that we still have a scaling of plastic dissipation. So we were shocked. Why did it work when we started to sum them together? Even in the grain boundary case, why did it work? The point here is that the summation kind of worked because the dissipation follows a power law. The plastic dissipation in some way will follow a power law as a crack keeps to grow. But E delta J stays the same way and it adds up. And so if I grow from crack from 0 to 1, I have an increment in jump in J, right? That goes from 0 to 1. In this case, 1 to 2 shown here, right? So I get 1 to 2 jump.
Yeah.
This 1 to 2 jump is basically what we're getting here in this case. And we add when I go from 2 to 3, 3 to 4, 4 to 5. That jump, I'm not running crack all the way to 3 and doing, my unit event is always this. And I'm only changing D and theta. So the plastic dissipation is also in a way incremental form. And that tends to capture the addition of the plastic increment as well. But I still don't have a very good explanation. I'm still with you, I understand your point. And the same thing I have myself as well. Why does it work so good? We add up these delta J's and they seem to be the total J delta A curve, where the explanation of rising delta J in ductile fracture comes from the idea of large-scale plastic dissipation. So it seems like every time this plastic dissipation we have captured in every unit event also adds up. But then why does it add up in a linear fashion when it's a power law? So we still need to look at more analytical part into it to come up with the idea why does it work, if it works.
Okay. Any other questions from the audience?
Shyam, I have a question.
Yeah, go ahead, Sumit. Yeah.
Yeah, Ankit, does the crack have a choice of not making the jump? So what I want to ask is time involved here? So would you be able to model crack arrest with this?
Well, with the finite element,
No. With this directed
graph model.
It seems to me that you are basically finding the path that the crack will take in order to fracture the specimen.
Right.
So what happens if the crack actually doesn't fracture the specimen and stops somewhere in between? Do you have that built into the model that the crack can at some point not choose to make a jump anymore?
Not until the micro. In this, I see your point, and it does happen in circumstances. In this case of predicting the model, unless the microstructure tells it don't grow, it got to grow. That's the one part, because we're assuming that's going to always follow the microstructure. So we did one of them, like we try to analyze that if there's a grain boundary case, if I have all of a sudden I have a grain boundary step that just goes 90 degrees. So it goes asymptotically up, right?
Right.
So in that case, it can capture an arrest, but an arrest is coming from microstructure. But in some case, when we are loading the material, it gets trapped for some other reasons, largely driven to plasticity, because the fracture is history dependent. If largely driven by some weird thing in plasticity in the material, then yeah, it cannot predict.
Right.
We do need the unit event to we need to know all the unit circumstances to work.
Right. Thank you.
Okay, so it looks like we don't have any more questions. So in that case, I would like to thank Ankit for accepting the invitation and delivering this talk. So Ankit, thank you very much. So if there are no questions, I'm closing the meeting now.
Thanks, Shyam, and thanks, Sumit, for inviting me again, and thanks for everyone for attending.
Thanks, Shyam.
Yeah, thanks everyone. Bye.